Alrighty, everybody. So this is 2-4 complex numbers. So our objectives, our essential questions today are to work with imaginary units. So what are imaginary values, complex numbers, to be able to do operations with them. So number 2 here, add, subtract, multiply, and divide. To be able to use what a complex conjugate is to write quotients, and then to be able to find solutions to quadratics that aren't real. So we've talked about what solutions could look like there if they're real, but we also need to talk about imaginary solutions. So we're going to be talking through all of those different things throughout the course of this video. So we can talk to you a little bit about that. So let's talk about the imaginary unit first of all. What is that defined to be, this I thing? So I is defined to be, and maybe you remember, the square root of -1. So it's taking care of all of these negative values. So I is defined to be square root of -1. There's no real number that can be squared that's going to equal -1. So that's why we call that the imaginary unit. So there is no real number that can be squared to get -1. So that's physically impossible. There's no way that that can happen. So we call that the imaginary unit then, so I. Now when you square I then, so the square root of -1 times itself, you get -1. So by definition, I squared then is -1, which is going to be a super helpful definition for us moving forward. So that's something to hang on to. So if the way we write complex numbers then, we use this A and B. So A and B, the complex numbers A plus BI, is said to be written in what we call standard form. So when you look at complex numbers, there's sort of a standard that we write. So standard form is this A plus BI. So there's a real part and there's an imaginary part. So let me give you some examples as we go through. So A plus BI would be something like 3 plus 2I. The real part is the 3, this is the A, and the imaginary part is the 2I, so the B would be the 2. So that would be a standard form complex number. So there's a real part and then there's an imaginary part. If the B is 0, meaning the second part, if the B is 0, that number then is just a regular old real number. So I'll give you an example as we keep going. So that's just, there's no imaginary part, in other words. If B is 0, there's no imaginary part. So that would be like if it was just 3 plus 0I. If there's imaginary part is 0, then it's just a pure real number. So there's no imaginary part. If the B isn't 0, so think about that, then it's called an imaginary number. So if the B isn't 0, then we call that imaginary because it has a real part to it. So like that 3 plus 2I again. So if you have something like that, they call that complex number imaginary. If the B isn't 0, but the A is, so what if it just has a BI? There's no real part. They call that a pure imaginary number. So just kind of some terminology just so you're familiar with it. A pure imaginary number, that would be if there's no real part at all. So say in this number, if it was just the 2I and the A part was 0, they would call that a pure imaginary, meaning there's no real part to it at all. Just some things for terminology. Let's talk about powers of I for a second. So we are going to be simplifying things that have different values or different powers of I as we go through. So I want to see if we can come up with some patterns to talk about what these values are. So we know what the basic definition is, and we said I squared is equal to -1. What I want to do is kind of keep going up the line here. Let's talk about I cubed. So we're going to talk about it as a product of, not T, my goodness, I to the second times I to the first. Why am I doing that? Well, then I can use what I have previously to help me define this. So I squared is equal to -1 times I cubed then is the same as opposite of I. Maybe this looks familiar from last year. I to the fourth. Let's keep getting higher powers. I'm going to write that as I squared times I squared. I think that's the easiest way to do it. Because remember, when you use your exponent rules, if you multiply two things with the same base, you add the exponents. So that's equal, it's equivalent, but what is I squared? Well, it's -1. So -1 times -1 would be 1. So I to the fourth is 1. Well, what if we go higher than that? Let's try I to the fifth. You're going to see why I'm putting it over here in just a second. So I would add these. So make sure that you're adding these off to the side so you have some examples of this. There's acres of space at the end of the section if you need more room for examples. So I to the fifth, I'm going to write that as I to the fourth times I. So again, because you add the exponents, it's equivalent. Why am I doing that? Well, I to the fourth, that's 1 times I, just I. Interesting. Okay, let's try I to the sixth. I'm going to break that up as I to the fourth times I to the second. I to the fourth is 1. I squared, remember, back over here, -1. Oh, so that's -1 then again. How about I to the seventh? I to the fourth times I to the third. Well, I to the fourth is 1. I cubed, we already did that. That's -I. And look at that. I to the seventh is -I. I to the eighth, I to the fourth times I to the fourth. 1 times 1 is 1. Look what happens. Looks like we have I, -1, -I, 1. I, -1, -I, 1. And it keeps following through this same pattern. So if I did I to the ninth, could you predict what that answer would be? Well, it should be I, because that would come from I to the eighth times I. You could do the arithmetic. How about I to the 10th? Oops, not -I, -1, right? Following the pattern. So it would be like I to the eighth times I squared, so -1. How about I to the 11th? Well, that would be like I to the eighth times I cubed. We're back to that I cubed, so -I to the 12th. I would do 8 and 4. Back to that 1, and it keeps cycling through. So we should be able to figure out bigger and bigger powers of I based off of what that pattern is, so we can do some simplifying and solving. Kind of a cool thing to be able to deal with. So we'll look at powers of I. Another thing to keep track of is like, where do these numbers fit into our whole number scheme, these imaginary things? So if we take all the real numbers that we know from before and put it together with all of these imaginary numbers, they form what's called the complex number system. So you're either real or you're imaginary. That forms this what we call complex number system. So when we look at that, that's the set of all of the real numbers, so everything that we had from our real number system, and the set of imaginary numbers, and we put those together, and that forms for us the complex number system, so all together. So we have real and imaginary. So when we can do operations with them, we can put them together. We have both of those parts. So two complex numbers, so if we're going to try to do some operations here, written standard form, if they are equal to each other, if and only if this happens. Well, think about it. If you have one number that's supposed to be equal to the other number, what would have to be equal? Well, the real parts better be equal to each other. So the real parts, the A and the C, so the real parts would have to be equal. And then what else would have to be true? Well, of course, the imaginary parts have to be equal. So the B would have to be equal to the D. So the imaginary parts of those numbers would have to be equal as well. So we're going to be using that too when we're solving and doing other operations with this. So the rest of what we're really going to talk about in the video here today is to do some operations. What can we do with these imaginary numbers, and go through and talk about that. So operations with complex numbers. Basically, if you're going to add, you add the real parts and then you add the imaginary parts. So you're adding each of those separately. So think of it like terms. So you add the real parts of the numbers, and then you add the imaginary. So you're doing each piece with it what it's alike with. So we're going to add the imaginary parts and we add the real parts. So let's try one just so you can see what we're talking about. If you didn't even know what I meant, you could probably do this. So we're going to add some examples. So please pause and add as you need to. So here's two complex numbers like A plus BI and another one C plus DI. If I kind of do some sorting and organizing here, I can look at my real parts, I can look at the imaginary parts, and I can put them together. So the real parts of my number 7 plus 5 would be 12. The imaginary parts of my number 3 minus 4i would be minus I. So this complex number together, if I add, would be 12 minus I. So we're just adding reals and we're adding imaginaries. Well, then how do you suppose you subtract two complex numbers? Well, exactly the same thing, right? You subtract the real part. So we subtract the real parts of the numbers, and then you subtract the imaginary parts. So we do the same thing. So again, if you didn't even know what imaginary numbers were, you could still do exactly the same thing. So you could just put like terms together and you would be just fine. Now be careful though, with subtracting, we got to be careful with our signs. So just to kind of sum up adding and putting these numbers together, we have identities and inverses for adding and subtracting. The additive identity means what number can you add to any complex number to get that number back? Well, that would be 0, the additive identity. If you take a number and you add 0 to it, you get the exact identical number back. That's the additive identity. Additive inverse, which is what we're going to use for subtracting, is what number can you add to any number to get 0? Or in other words, maybe a better way to say is what is the opposite? Additive inverse means the same thing as the opposite of the number, additive inverse. So the opposite of a plus bi, the opposite of it is this. Take a negative out front of a plus bi. So we distribute that minus through to both. It would be opposite of a minus bi. So the additive inverse or the opposite of something. So just take the opposite. So we usually think about that when we talk about subtracting. So let's take a look at what I mean by that. So take a look at the subtracting example. Go ahead and add that. 3 plus 4i minus 5 minus 3i. So we can think of this as adding the opposite there. So we want the opposite of both terms. So that subtraction, remember, has to go to both things. So 3 plus 4i minus 5 plus 3i, so minus a negative. So we just have to be aware of your signs as you do that. All right, so real parts together and then imaginary parts together. So we subtract the real parts, that would be -2, and the imaginary parts end up being adding, subtracting a negative, 7i. So we get our final complex number, -2 plus 7i. So adding and subtracting, pretty straightforward. I think it's pretty much what you think it would be. On next to what if there's multiple numbers? It's not just 2. Well, just do your order of operations. So this is the one that's actually in your note-taking guide. We have a subtraction and an addition. Notice this last one is what we would call a pure imaginary number. There's no real part at all. So what I like to do whenever I see that subtraction, I like to write out and distribute that minus all the way through. So just being careful, we're subtracting everything. Now we're going to sort and organize here. I have my imaginary parts, and then I have my real parts, and I'm going to put everything together. So my real parts, that would be 2, and then for my imaginary, it looks like I have 6i together over here, but then I'm subtracting 6i. That means I have 0i left, or just actually the number 2. It just ends up to be a real number. Totally fine. Doing operations with complex numbers, you can end up with either just a real or one of those pure imaginaries. Totally fine. So we can perform multiple operations. Okay, on to new operations. What if you multiply? Well, you multiply exactly how you'd imagine binomials should be multiplied together. Complex numbers are binomials. So how do you multiply 2 binomials together? You use FOIL. So that first, outside, inside, last. It's the distributive property. You're going to multiply these 2 together. So we're just doing the distributive property. It's the same as what you would assume even if you didn't know what the i's stood for. So a plus bi times c plus di. So first, outside, inside, last. Let's take a look at an example of that and how that might simplify. So here's the one that we're going to try, the one that they gave you. We're going to go ahead and do FOIL. So first, 5 times 3, that would be 15. Outsides, that would be minus 10i. Insides, negative 18i. And then last, negative, negative, so be careful. That would be plus 12i squared. Okay, let's talk about simplifying. I think most people would kind of immediately look at those 2 I terms in the middle and say, yep, I can put those together. So minus 28i. Now, the thing that we have to remember that's kind of unique about complex numbers is that this I squared is something. Remember, I squared is equal to -1. So we can make that substitution. So instead of just having a plus 12 there, what you actually have is a 12 times -1. Or a negative 12. So 15 minus 28i minus 12. In other words, if you have a negative or an I squared, what it really means is it's a -1. So it's changing the sign of your term. So my term was a plus, it became minus. If this term initially had been a minus, it'd become a plus. Well, what does that mean for our expression? Well, now I actually have real parts I can put together too. So 15 minus 12 would be 3 minus 28i. I have a real part and I have an imaginary part. So that's kind of a unique thing about multiplying with these numbers, with these complex numbers. We can simplify those powers of I. Okay, I want to do a little bit more with multiplying because there's some things we want to talk about. So I'm going to zip through some of these examples. I know these are all added, so feel free, try them, kind of pause the video, try them, and then check your answers so we can go through and do that. And I'll talk through the explanation for each one just to make sure that we're good to go. So these are all added examples. Feel free to add them wherever you like. We have plenty of room. First one is just a pure or just a real number times a complex number. So we can just distribute. It's exactly what you would assume it to be. Negative, negative would be plus 10i. So we get this complex number solution. So you can just distribute. All right, next one, letter B, just like the one we were doing before, FOIL. So first, outside, inside, last. Looks like we have 6 for first, plus 6i for the outsides, minus 12i for the insides, minus 12i squared for the last. And then let's see what we can do to put our like terms together. Now remember, this I squared again is equal to -1. So that's like a -12 times a -1, which in effect makes this a plus 12. Some people get pretty quick at picking that up, and then they can put their like terms together. So we've got a 6 and a 12, so that would give us an 18. And then let's put together our i's. That would be a minus 6i. We ended up with an imaginary number. Okay, I wanted you to notice what happens with letter C. See if you can notice what's true about these two binomials. They're identical except for what? Just their sign in the middle, right? Watch what happens when you multiply two binomials together where they're exactly the same except for their sign. So first would be 16. Outsides would be a minus 20i. Inside's a plus 20i. And then last would be minus 25i squared. All right, so cool. Watch what happens. Look on the inside here. The oi, checking your oi. The inside and outside terms, they're identical except for sign. So what happens to them? Well, they're 0. That's nothing left. You lost those I terms completely. That will always happen when you multiply something times the exact same binomial, but with the opposite sign in the middle. Let's look at the last term. Remember, your I squared is -1, so -25 times a -1. That would be a plus 25. So you can put that together with your other real number, and you end up getting grand total of 41. You ended up with a real number answer. So kind of cool. That's going to play a part in what we do next in dividing. All right, what does it mean if you have a binomial squared? Well, that means you take your binomial and you multiply it times itself. So you're still doing FOIL. Don't fall into that trap of Algebra 1 where you just square both things. It's actually FOIL. So first, outsides, insides, and last. Kind of cool in this situation. Make sure you multiply those number parts too. 2 times 2, 4, right? 4i squared. Look at what happens when the binomials are the same. You end up getting the same term on the insides and the outsides, but instead of them adding to 0 like they did in the last one, they're exactly the same, and so they're double. There's 2 of the same thing. All right, so putting the i's together, that would be 16i. Remember here, I squared is -1, so 4 times -1 ends up being a -4. So a -4 together with a positive 16 would be 12 plus 16i. So kind of a cool way to be able to go through and just double check with our multiplication. All right, so moving on, complex conjugates. We need this to be able to do division. So we're going to talk about what a conjugate is. A product of a number and its conjugates is always a real number answer. And that's exactly what we were talking about in this last example, right down our second to last example, where we multiplied something by what we call its conjugate. We ended up getting a pure, just real number situation, which is super helpful when we're dividing. So in order to be able to do division, we end up doing something like multiplying by the conjugate. So we're going to multiply both the top and the bottom by the conjugate. So we multiply by the complex conjugate. So we need to make sure we know what that complex conjugate is. And I think you've heard of these before. I think you guys did these previously. If you have a expression a plus bi, its complex conjugate, complex meaning that's kind of the number it is, conjugate meaning opposite in sign. So the conjugate is a minus bi. So it's the exact same expression with the opposite sign in the middle. Because what happens when we multiply these two together, you get just strictly a real number answer. In other words, just a nice, rational, real number to deal with. So let's see where that comes into play. When we do division, so let's take a look and see if we can write it out. 1 plus I divided by 2 minus I. And we want to simplify that and write the answer in standard form. We need to have something to deal with this denominator, this 1 or 2 minus I. I is a radical, right? We can't have a radical in the denominator of a fraction. It's not easy to work with. It's not user-friendly. So how do we make this from being an imaginary thing to being a real thing? Well, we multiply the top and the bottom by the complex conjugate. It's kind of like what we do for rationalizing. It's exactly the same, actually. It's like rationalizing a fraction. If you have a radical in the bottom of a fraction, you multiply top and bottom by that same radical. Exact same idea here. We multiply by its complex conjugate. So 2 plus I. Notice the expressions are exactly the same, just opposite sign. This was a minus, so my complex conjugate is a plus. Okay, so what does that mean then? Well, we're going to actually do this FOIL. We're going to multiply it out. All right, so let's do that. So we're going to do FOIL on the top and on the bottom. So whenever you're doing division, dividing these complex numbers, multiply by the complex conjugate if you have a binomial in the bottom. All right, so let's do the denominator first. So first we get 4. Outsides we get plus 2i. Insides you get minus 2i. And then last we get negative I squared. All right, well, how is this going to help us make a nicer number? Look what happens on the inside, the 2 and minus 2. So that adds to 0. That I part is gone. And remember, I squared, hey, that's negative 1. So we have minus a negative 1, which is just regular old plus 1 then. So 4 plus 1, our denominator is now 5. Isn't that way better than what we started with? Sure is. So we end up with this nice, awesome number in the bottom to deal with. Okay, the top, we just have to deal with it. Do your FOIL. So we've got 2 for first. Outsides is I. Insides 2i. And then last plus I squared. Just simplify and put your like terms together. So I squared, remember, is negative 1. So we have a 2 minus 1. So 1, and then put your i's together. 1i plus 2i would be 3i. So look, we did our division and we ended up with this nice number. Now, how do we get it into standard form? Standard form, remember, is the a plus bi kind of form. All right, well, we're going to just take a look at what the real part of the number is. 1/5 plus the imaginary part of the number, 3/5 I. In other words, take everything in the top and divide it by the bottom. Instead of leaving it together as a single big fraction, we can look at the real part of the number then, and then the imaginary part separately. So we have those two pieces. So if you have a division, we can undo it by multiplying by the complex conjugate. Now let's take a look at one other division example before we get into dealing with radicals. So there's a lot of just working on what happens in these sections. So making sure we understand what the different operations are. If we're going to divide in this situation, so please add this one, 3 minus 6i and dividing by just 7i. We don't need to worry about complex conjugate necessarily, although you can. We don't really need to worry about the 7. The 7 isn't the issue. The issue is this I remember, is the square root of negative 1. Can't technically really leave that in the denominator and have this standard form kind of answer. So what would I do? Well, I can multiply really just by the I. Could you multiply by negative 7i? Yes, that would be its conjugate. Same thing, but opposite sign. But the 7 is fine. You're just going to have to reduce it out. Just multiply by the thing that's causing the issue. So we multiply kind of like the radical by itself. Watch what happens. In the denominator, you get 7i squared, which seems like you still have an issue, but remember, I squared is negative 1, so really in the denominator, you just have a 7. We're shooting for a whole number here, so we can simplify it out and look at the real part and the imaginary part. In the numerator, just distribute. So we have 3i minus 6i squared. Remember, again, I squared is negative 1, so negative 6 times negative 1, that would be a regular old 6. And then plus 3i. Now, why did I put it that way? Well, if we want to write it as real and imaginary, it's a lot easier to put that 6 first and then plus 3/7 I. So we have the real part and the imaginary part of that number. So it's kind of a nice way to look at it. So even if we just have these values, oh, did I mess that up? Oh, I did. I forgot my minus. Pardon me. Negative. Sorry, these are both minus. Double check my work there. So 7 times -1. I forgot my sign on the 7. So -7 at the bottom. So -6/7 minus or plus negative, whichever way you want to say it, 3/7 I. So, yep, it's super easy. Even I just did it. Keep track of your signs so you know what's happening. Okay, to finish up, we're going to talk a little bit about complex solutions then of quadratic equations. What happens if we end up with these imaginary solutions in our quadratic equations when we're solving? So if you have a positive number and you're trying to take the square root of it, we have no issues, right? We talked about domain, taking a square root of something that's positive, not an issue. But what happens if you're trying to take the square root of a negative number? Like this. Well, gosh, that's hard to deal with. So what we try to do, if we're going to simplify with it, is break it down into a product. Square root of -1 times square root of that positive value. That way we can think of it as square root of -1 is I times the square root of that number. Get that -1 out from underneath the radical. It's so much easier to simplify then, and we'll be able to deal with then all these different values that we have to work with. So the idea is to avoid these problems dealing with square roots. If you get everything into this standard form first, so that form that we just talked about there is standard form for the radicals, do this first, that standard form, and then you're going to be able to simplify with those quadratics or whatever you're doing to solve right away. So writing those numbers in complex number into standard form, you're taking out that -1 and writing what's left. So we're getting it into standard form first. So for example, just going to add this one really quick. If you have square root of -3, instead of thinking of it that way, think of it as the product. -1 times 3, because then we can write I square root of 3. It's much easier to work with the numbers. We can put all the real parts together then. All right, so let's try working with that first, and then we'll get into actually solving quadratics and things. So take a look at what I mean by, let's get the I's out of there. For each of these, let's rewrite it as the square root of -1 times the square root of 14, square root of -1 times the square root of 2. Remember, when you multiply two radicals together, you're just multiplying what's underneath. So this is completely legal to do. But what does that leave you with? In each of those cases, it's I times that radical then, right? Because every time you see square root of -1, that's an I. I'm going to rearrange here. I times I, that's I squared. Square root of 14 times the square root of 2, that's a square root of 28. Now I can work with what I have left. So hopefully you remember how to simplify radicals here. 28, now that's a real number. I can work with that. What perfect square divides into 28? Well, that's 4 times 7. And remember, I squared, that's -1. I can do that substitution. So square root of 4 is 2. So 2 times -1 times the square root of 7, I have a -2 square root of 7. It's so much easier to simplify if I just take out those negatives first, get them taken care of right away. All right, let's try another one. So square root of -48, that would be -1 times 48 minus, and again, -1 times the square root of 27. So I'm doing that again to separate the real part from the imaginary part. So I times the square root of 48 minus I times the square root of 27. Now let's go ahead and simplify the radicals like we normally do. 48, what's the biggest perfect square that divides into 48 evenly? Well, that's a 16, so 16 times 3. We're going to do the same thing for the 27. Biggest perfect square that divides into 27, 9. And then let's keep going. We're going to simplify. So square root of 16 is 4. So 4 times I like to write it in this order. This is my preference. Whole number part, imaginary, and then radical. It's just easiest for me to read. Square root of 9 is 3. So 3I square root of 3. All right, now here's what I need to ask you. Are these like terms? Remember, the only way you can add or subtract is if they're like terms. What does that mean for the radical? Same number under the radical symbol. It's called the radicand. Love saying that, the radicand. So you have 4I square root of 3 minus 3I square root of 3. Like terms. They both have an I they both have a square root of 3. So 4 minus 1 leaves you with 1i square root of 3, or just I square root of 3 if you prefer. Totally fine. So it's a lot easier to simplify, moral of the story here, when you have those i's out of here. Alrighty, so let's try this operation. See if we can make it easier by dealing with the i's. Let's give this one a whirl. Remember what it means to square something. This is a common error that people make. So 5 minus, and then we have 5 minus. It's multiply times itself. Now, I don't want to multiply times itself, though, with this written in here like -4. So let's see if we can make that radical a little bit easier. Take out the -1. So square root of 4 is easy by itself. That's 2. Square root of -1 is I. So that's really just a 2i. So really what you have is 5 minus 2i times 5 minus 2i. Much easier scenario to deal with then, right? When we're looking at these, to have it just in that standard form. Okay, now we can do our FOIL. So first, 25. Outside's minus 10i. Inside's another minus 10i. And then plus negative 4i squared. All right, so it's the same multiplication as what we were doing before. So when we put them together, we can put together our I terms. That would be a -20i. And then here we have a 4 times a -1. All right, so 4 times -1 then would be a -4. I can put that together with my 25s. That would give me 21 minus 20i. So really convenient if we just take care of those negatives first, put it in standard forms, and then we're able to simplify. Okay, so why did we just do all that? Let's see if you can solve a quadratic. All right, so here is one of these equations where we're solving to find the zeros, the solutions to this equation. So it's degree 2, which means it's a parabola. How do we solve those? Well, if it's equal to 0, we factor if we can, and our backup is quadratic formula. Now, if you try to factor this one, what you're going to notice, it is not factorable. There is no way we can plug these in and get anything that is going to be easy numbers for us to factor. So we're going to use the quadratic formula. Remember, that's dealing with ax squared plus bx plus c, the a, the b, and the c. So my a value is 8. My b value is 14. My c value is 9. And I can actually solve and watch what happens in terms of these imaginary solutions. So x equals, so remember our little quadratic formula, right? X equals opposite of b plus or minus square root b squared minus 4ac all over 2a. That's going to be on the Grammy someday, I bet you anything. Not really, that was horrible, but it's okay, because it goes the pop goes the weasel sign to help you remember. So x equals opposite of b, so opposite of 14, plus or minus square root b squared, 14 squared. I just go ahead and square it right away. 14 squared is 196, minus 4 times a, which is 8, times c, which is 9, all over, that whole thing over 2a. So 2 times 8, so 16. And then we just simplify. Let's look and see what happens on the inside here. This discriminant, remember? So the discriminant number underneath the radical. So we have -14 plus or minus square root. The number under the radical, go ahead and do your arithmetic there, -92 all over 16. Well, why are we talking about this then? Well, it's -92. What does that mean for your graph? Do you have real solutions? No, it's 2 of these imaginary solutions. So does your parabola cross the x-axis? Nope. I encourage you to go ahead and type this equation in, do a zoom fit, and look at the calculator. You're not going to have any x-intercept points. There are no real zeros to this equation. So what would I do? I would just simplify this square root of -92 as best I can. So I'm going to take out that negative, that standard form, and then I'm going to try to simplify that 92. I believe 4 divides in there. Double check for me. So 92 divided by 423. Believe that looks good. And then we have our square root of -1, which is an I. Square root of 4 is 2. So 2i square root of 23. Simplify as best you can. They're going to be imaginary. We're not having real values here anyway. So x equals opposite of 14, -14, plus or minus 2i square root of 23 all over 16. All right, the only other thing I can say we can probably do here is see if we can reduce this fraction at all. So let's see if we can write it out. So -14/16 plus or minus 2 square root of 23 over 16i. We're going to write this out. I think we can reduce a little bit then, right? -7/8 plus or minus square root of 23 over 8 times I, right, if we can reduce each of those fractions. Some people might just leave it as a single fraction, negative 7 plus or minus square root of 23, or I square root of 23 over 8. You can decide where you like the I best. You can leave it together as well. Imaginary solutions, though, the graph doesn't cross the x-axis. Lots of big stuff to talk about with complex numbers, remembering what we were doing from before. Hopefully these things come back and you can do these operations, and we'll talk about some things you can do on the calculator as well. Imaginary. So we'll be back at it talking about some examples together on the assignment, and we'll be doing some work with those.